Hello, everyone. Hello, Anjali, Meghna, Yash, Shreya. Just a second, students. Hello, Pradeep, Yash. Just a second. Hello, Samir. Okay, so let's start now. Students, this is our first session of modern physics. Okay, so in this session, basically, we are going to discuss numericals. Okay, so you can see the first question: photoelectric effect experiments are performed using three different metal plates P, Q, and R, having work function 2 electron volt, 2.5 electron volt, and 3 electron volt respectively. Okay. So a light beam containing wavelengths of 550 nanometer, 450 nanometer, and 350 nanometer with equal intensities illuminates each of the plates. So we need to check which of the following VI graph is correct. Okay. So first of all, let me give you idea about the photoelectric emission, and after that we'll talk about this question. So let's start now. So first of all, you know very well about this equation. K max is equal to what? Here you can see K max, maximum kinetic energy of the ejected electrons, I can say. K max is equal to h nu minus h nu naught. Here h nu naught is what? That is the work function. Okay, so suppose here we are taking h nu naught as a phi. Okay, phi is the work function. Okay, here this one is work function. So here K max is equal to what? H nu minus phi naught. Okay, suppose if you're taking this one as a phi naught. This is the equation. Okay, here H nu is what? Energy of photon. Energy of photon. And you know very well about here K max, that is the maximum kinetic energy of the ejected electron. Student, if this is the plate, okay, just a second. This is the plate, and suppose this is the incident photon. Okay, and if energy of incident photon is h nu, okay, and the work function of this metal plate is phi naught. So if h nu naught, energy of this photon, is more than that of what? Work function of this metal, only in that case this metal plate will eject electron. Only in that case, when h nu is what? More than that of phi naught. Okay. One more thing, student, if we'll talk about the stopping potential, stopping potential, or you can say maximum kinetic energy is equal to what? Potential energy, and potential energy is what? EV naught. Okay, suppose if electron is accelerated, suppose if a potential difference of V naught is applied across the electron, then the potential energy of that electron is given by this EV naught. Okay, and if entire kinetic energy is converted into potential energy, so K max is equal to EV naught. Okay, from this here V naught is equal to what? Here V naught is equal to K max upon E. Okay, maximum kinetic energy divided by E. This is what? This will give you the value of V naught. And here V naught is what? V naught is stopping potential. V naught is stopping potential. So we can see here stopping potential is basically depending on what? Maximum kinetic energy. Okay, it is only depending on the maximum kinetic energy of the ejected electron. Okay, now next point. And what about the kinetic energy? This is the equation of kinetic energy. No, K max is equal to h nu minus phi naught. This one. Okay, this is maximum kinetic energy. So this maximum kinetic energy is depending on what? H nu. Okay, more the value of h nu, more will be more the difference of h nu minus phi naught, more will be the maximum kinetic energy. Okay, that's great. So, and it is also depending on frequency. Suppose if frequency increases, suppose frequency of photon is increasing, so in that case kinetic energy will increase. Okay, maximum kinetic energy of the ejected electron will increase. And if kinetic energy is increasing, so obviously stopping potential will increase. Okay, now next important point. What about the what about the intensity? What about the effect of intensity on maximum kinetic energy? Okay, so we know that student, intensity. Suppose if intensity is increasing, so simply we can think number of photons falling on the metallic plate is increasing. If we assume frequency as a constant. Okay, suppose f is constant, frequency is constant, and intensity of the photoelectrons is increasing. So in that case, number of photons falling on the metallic plate is what? Increasing. Okay, number of photons increasing, but no change in frequency. And if frequency is not changing, so I can say that maximum kinetic energy is not changing. Why? Because we know that phi naught is constant quantity, work function of a metallic plate is constant. Okay, and here frequency is also constant, so maximum kinetic energy is also constant. Okay, and if maximum kinetic energy is constant, in that case stopping potential is also constant, because stopping potential is equal to K max upon E. I can say that. It means we can see here, if intensity is changing but stopping potential is what? Same. No change in stopping potential. Okay, so whenever intensity is changing, so that will change the photocurrent. Okay, because we know that photocurrent is directly proportional to the intensity. As the intensity increases, photocurrent will increase. So I can say here photocurrent is directly proportional to I. Okay, so as the intensity is increasing, photocurrent is increasing. Okay, photocurrent is increasing, but no change in maximum kinetic energy, no change in stopping potential. Okay, these 2 points are very much important. Okay, now let's talk about the effect of frequency on stopping potential, maximum kinetic energy, and we'll talk about number of photons as well. So let's see here now. Can discuss here. Okay, so suppose intensity is constant. We took here I as a constant. Okay, intensity is constant, but suppose frequency is increasing. If frequency is increasing, it means energy of photons is increasing. E is equal to what? H into nu. Okay, F is increasing, or you can say here either we can use nu or this mu or this F to represent the frequency. So if mu is increasing, so I can say that energy of photons increasing. And if energy of photons increasing, so tell me this difference is increasing, no? K max is equal to h nu minus phi naught. Okay, so this is work function, and that is constant. That is constant for particular metal, particular plate. Okay, this one is constant. And this frequency is what? This frequency is increasing, continuously increasing. Frequency is increasing, so this overall difference is increasing, na? Okay, so we can see that here maximum kinetic energy is increasing. Okay, kinetic energy is increasing. And what about the stopping potential? Stopping potential is K max divided by E. So here if K max is increasing, so I can say that stopping potential is also increasing. Okay, it means yeah, energy of photon is E is equal to H into nu. H is Planck's constant, mu is the frequency. Okay, so here frequency is increasing. If frequency is increasing, K max is increasing. K max is increasing, it means stopping potential is also increasing. Okay, these two points are very much important. Okay, so now we can discuss this question. Okay, now we can easily answer this question. So student, in this question you can see we have given three plates, three metallic plates P, Q, and R. Okay, and their work function is given. So suppose first metallic plate here is P, Q, and R. Work function of first metallic plate is, I can see 2 electron volt. For this one, suppose phi is given, work function is 2.2 electron volt. Here 2 electron volt. For this one, 2.5 electron volt. And what about the last one here? You can see 3 electron volt. Okay, fine. So for this one, 3 electron volt. So suppose this is the metallic plate. This one is the metallic plate, and here light is falling. Suppose this is the light. Okay, and a student, this light beam containing 3 different wavelengths: 550 nanometer, 450, and 350. Suppose 550. Okay, 550, 450 nanometer, and 350. Okay, sure, surely we'll do that, David. But right now, it's a session of modern physics, so it's a first session. So basically, in these sessions, we only talk about the numericals, previous year JEE numericals. Okay, so and right now we're discussing here question. So please try to focus here. So student, you can see this beam is containing 3 wavelength: 350, 450, 550, and 450. And we need to check which of the following graph is correct. So student, let's find out the energy of photon first. So see here, energy of photon is what? E is equals to h nu, and frequency is what? C by lambda. Frequency is C by lambda. Okay, and student, here h is constant, C is constant. Okay, when you'll put the value of h and C, and after solving you'll get 1240 divided by lambda. Okay, but this lambda should be in terms of nanometer. Okay, this lambda should be in terms of nanometer. So we can directly use this formula to get the value of what? E, energy of photon. Okay, 1240 divided by lambda, but this lambda should be in nanometer. So let us calculate for first wavelength. Here first wavelength is what? Here you can see 350 nanometer. So here E1 is equal to what? E1 is equal to 1240 divided by what? Divided by here 350 nanometer. 350, and after solving 350, so after solving we'll get around here 3.54 electron volt. We'll get here 3.54. We can do the calculation, 3.54 electron volt. Okay, electron volt. So students, now next one, what about E2? For E2 we can take 550. Okay, wavelength 550 nanometer. So after solving, we are getting here around 2.25 electron volt. Similarly, we can find out for third wavelength. You can see third wavelength E3, that is equal to 1240 divided by what? Third wavelength is 450 nanometer. So for this one, we'll get around this is what? 450. We'll get around 3.7 something electron volt, 3.75 around. Okay, 3, or just a second, it should be here to 3.54, 2.5, it should be 2.5. Okay, 2.5 electron volt. Now we can compare. Okay, now we can compare for compare with the work function. So for first metallic plate, work function is 2 electron volt. Okay, energy of this electron volt. See, energy of when photon of 350 nanometer is falling, then energy of that photon is 3.54. It, and you know that whenever energy of photon is more than that of work function, only in that case metallic plate will eject electron. Okay, so for metallic plate P, work function is 2 electron volt, and for wavelength 350 nanometer, energy of photon is 3.54. So this is more than that of work function of metallic plate P. So obviously in this case, metallic plate will eject electron. Okay, in case of 350 nanometer. Okay, in case of what? 350 nanometer, metallic plate P will eject electron. Okay, so for wavelength 350 nanometer, metallic plate P will eject electron. Now what about wavelength of 550 nanometer? In case of 550 nanometer, energy of photon is 2.25 electron volt. Still this energy is more than that of work function of metallic plate P. So it means metallic plate P will eject electron. Okay, so for wavelength 550 nanometer, P is what? P will eject electron. What about the last one here? Wavelength is what? 450 nanometer. Energy of photon is 2.75. That is more than that of what? That is more than that of work function of metallic plate P. So in this case also metallic plate P will eject electron. So here for wavelength 450 nanometer, here metallic plate P will eject electron. Okay, that's great. What about the metallic plate P? So student, for metallic plate Q, work function of metallic plate Q is 2.5 electron volt. Okay, and tell me this energy work function of this metallic plate is less than that of 3.54 and 2.75. So only in these two, only for these two wavelength, this metallic plate Q will eject electron, not for 550. Why? Because for 550 energy of photon is only 2.25. That is less than the work function of metallic plate Q, no? So it will not eject electron. So here metallic plate Q is ejecting electron for this one and this one. Okay, for this one, not for 550. What about for R? Work function of metallic plate R is what? 3 electron volt. That is only more. So here in this case, when wavelength is 350 nanometer, then the energy of the photon is more than 3 electron volt. So metallic plate R will eject electron only in this case. Only in this case. So you can see here, I can see that metallic plate P is ejecting electron for every wavelength, and metallic plate Q is ejecting electron for 350 and on 350 and 450, and metallic plate R is ejecting electron only for what? Only for 350 nanometer. So we can see that here we can see that here maximum kinetic we can say that here in photocurrent is maximum for what? Photocurrent is maximum for P, then Q, then R. Okay, so we can, so you can, in first diagram you can see first of all photocurrent of P is more than that of photocurrent of what? Q, then photocurrent of R, because metallic plate P is ejecting more electron than Q. Okay, and R is ejecting less number of electrons because it is only ejecting electron for 350 nanometer. That's the reason. Okay, now what about the stopping potential? Student, you know that K max is equal to what? Here first of all, stopping potential is equal to K max upon E. Okay, and K max is equal to H nu minus phi naught. Okay, so here from this relation you can see stopping potential of P is what? More than that of Q, more than that of R. Okay, because maximum kinetic energy for P is more than that of Q and R, because P having least number of what? Because P having less value of what? Work function. That's the reason. So option A is the answer. You can see for P more photocurrent, more stopping potential. For Q, you can see this is for Q, and for R less photocurrent and less stopping potential. So A is absolutely correct. Okay, here A is the correct answer of given numerical. Okay, now now we can talk about the next question. So let's see here. Okay, here you can see an electron in a hydrogen like atom is in an excited state. Okay, that's great. It has a total energy of minus 3.4 electron volt. So we need to find out the kinetic energy and the de Broglie wavelength of the given electron. Okay, so let's see here. So student, first of all, if we'll talk about the expression of kinetic energy is equals to what? K Z E square upon 2R. Okay, and what about the what about the potential energy? Potential energy is equal to what? Minus of K Z E square by R. And for total energy E is equal to what? Minus K Z E square by 2R. So students, you can see the magnitude of total energy and kinetic energy is same. K Z E square by 2R. Okay, that is the magnitude of kinetic energy, and that is same as that of the total energy. So their magnitude is same. So only difference between the kinetic energy and the total energy is what? Sign. You can see here here kinetic sign of kinetic energy is positive here, and for this total energy negative. Okay, so I can say that kinetic energy is equal to the magnitude of total energy, and here the total energy of the electron is given, that is equal to minus 3.4 electron volt. Okay, but we need only magnitude. So here I can say that we are getting plus 3.4 electron volt. Okay, so here kinetic energy is what? Plus 3.4. This is the answer of the first part. Okay, so student, be careful with this point. You can see kinetic energy is equal to what? Kinetic energy is equal to the magnitude of the total energy. Okay, see here, let me show you here. Kinetic energy is equal to the magnitude of total energy. Okay, and what about the potential energy? So student, what is the relation between the potential energy and kinetic energy? See here, kinetic energy is equal to kZe square by 2r na? Okay, and potential energy is what? Potential energy is minus of kZe square by r. So now suppose we can replace this part, we can replace this part by just a second, we can take here r square as well. Okay, this r square kz is r square. Okay, now this one. Okay, first of all, guys, you know that suppose if this is the nucleus, this is the nucleus, and electron is revolving around the nucleus. Suppose student, electron is revolving around the nucleus. So if electron is revolving around the nucleus, so which force is required? Centripetal force is required, na? You know that. And centripetal force is what? mv square by r. If electron is revolving around the nucleus, so centripetal force is required mv square by r. That's great. What about the and which force is providing the required amount of centripetal force? Okay, charge of this total charge of this nucleus is suppose z into e, and there is a electrostatic force of attraction between the electron and the nucleus, and that force is what? K e into ze divided by what? Divided by r square. Okay, and this force is providing the required amount of centripetal force. So let us equate them. So here mv square by r is equal to what? Kze square by r square. Now what we can do? You can see here, now here one r gets cancelled. So this is mv square and this is kze square by r. Now we can multiply both sides by 1 by 2. 1 by 2. Okay, so see, this is what? This is kinetic energy in a half mv square, and you can see here kinetic energy is equals to what? Kze square by r. Okay, so here we don't need to put here the r square, because student, you can see here kinetic energy is equal to kze square by 2r. Okay, similarly we can find out the potential energy and the total energy. So now we can replace this part, this one as a what? Minus p, minus p. See, because potential energy is what? Negative. So here kinetic energy is equal to what? Potential energy divided by 2. If we talk about the magnitude only, so this is the relation. Okay, these relations are very much important for your CBSE as well as for JEE. Okay, so kinetic energy is equal to potential energy divided by 2, and the magnitude of kinetic energy is equal to the magnitude of the total energy. Okay, so we got here the answer of the first part, plus 3.4 electron volt. What about the second one? Here you can see the second one, the de Broglie wavelength of the electron. So this one is extremely simple for you guys. You know that here de Broglie wavelength lambda is equals to h by p. Okay, in this given given here kinetic energy is given. Kinetic energy of the electron is what? Plus 3.4 electron volt. Na? Okay, and what is the relation between the momentum and the kinetic energy? We know that P is equal to what? Root under 2 km. Na? This is the relation between the potential energy and kinetic energy. Here K is what? Here K is the kinetic energy. So now here lambda is equals to h by P. Here P is 2 km. Now put here the value. H is Planck's constant. You know the value of H, 6.64 10 raised to power minus 34. And what about this kinetic energy? Student, here 3.4 electron volt na, but in calculation we need to take in terms of joules. So 3.4 into 10 raised to power, sorry, into 1.6 into 10 raised to power minus 19. Okay, because 1 electron volt is equal to 1.6 into 10 raised to power minus 19. Now put here. So this is 3.4 into 1.6 into 10 raised to power minus 19. And what about mass? You know very well here the mass of the electron. You can put the value of m here, 9.1 into 10 raised to power minus 31. And after doing entire calculation, you will get around 6.6 angstrom. Okay, you will get around 6.6 angstrom. Okay, this is the answer. Okay. So here lambda, so we got here the answer of the second part, 6.6. And what about the first part? For first part, 3.4 electron volt. Now move on to the last question of today's session. the work function of a substance is 4 electron volt. Okay, fine. This is the work function, 4 electron volt. The longest wavelength of light can cause photoelectron emission from this substance is approximately what? We need to do here the calculation and find out. So student, you know that E is equal to what? E is equals to hc by lambda. E is equals to hc by lambda. Okay, so after doing calculation, we'll get answer in terms of joule. Okay, but you need, if you need answer in terms of electron volt, so we can divide this entire thing by what? 1.6 into 10 raised to power minus 19. So here hc lambda, and let us divide this entire term by 1.6 into 10 raised to power minus 19. Okay, and after doing the calculation, we'll get answer in terms of electron volt. So student, we can put here the value of h and c, because here h and c constant. Okay, and so here this E is what? 12,375 divided by lambda. Okay, divided by what? Lambda. And here or you can say not lambda, here, yeah, lambda. So students, this lambda is equal to what? 12,375 75 divided by what? Divided by E. Okay, or we can replace this E by work function if you want. Okay, this will give you the what? This will give you the wavelength. This will give you the wave. And guys, one thing we can take here, work done directly in terms of what? Electron volt. This will give you the wavelength, but that wavelength will be in terms of what? Angstrom. Okay, angstrom. So students, tell me, we will get answer in terms of what? Angstrom. Here after doing calculation, we'll get answer in terms of angstrom. Okay, so tell me, we can put here the value of W now. What is W here? 4 electron volt na. So 12,375 divided by what? 4 electron volt. Yeah, 4 electron volt. And after doing the calculation, we'll get option C. Okay, yeah, option C is absolutely correct. So option C is the answer of this question. So student, first thing, if we'll talk about the dual nature, so guys, questions based on kinetic energy and potential energy is important. And guys, graphs related with what? Graphs related with photocurrent, frequency, and what? Stopping potential. Okay, so graphs based on these topics are very much important from dual nature. Okay, so you can prepare the this topic. Okay, or you can say graphs which is based on intensity and photocurrent, graphs between frequency and stopping potential. Okay, so now students, we can end this session. Okay, so see you in next session. So to know how Meritnation can boost your preparation, you can go through this URL. Okay, so thank you so much everyone. Take care. Bye bye. Thank you so much. Thank you. See you in next session.